Welcome to Ask and Learn.
In this problem, nitrogen gas is expanded in a polytropic process. We wish to calculate the work done and the heat transfer in this process. Now we assume that nitrogen is an ideal gas, the kinetic and potential energy changes are negligible, and constant specific heats can be used. The properties of nitrogen are its gas constant R 0.2968 kilojoule per kg Kelvin, and the constant volume specific heat CV is 0.743 kilojoule per kg Kelvin. So we can take the nitrogen in the cylinder as our system, and the system is closed since no mass crosses the boundaries. And hence we can write the energy balance equation for the system, E in minus E out is equal to the change in energy for the system, delta E. Now the energy in is the heat transfer, Q in, and the energy out of the system is the boundary work that the system does, W. And this is equal to a change in internal energy of the system, delta U. But the change in internal energy is due to the change in temperature. So that's mCV delta T, the change in temperature, T2 minus T1. So this is our energy balance relation for our system. We have heat in and work being done by the system, so the work is out of the system, and this causes a change in internal energy, mc delta T. Now we can use the boundary work relation for the polytropic process of an ideal gas to find the boundary work. The boundary work per unit mass, so little w, out of the system is equal to R times T1 over 1 minus N, all multiplied by the ratio of the pressure of state 2 over the pressure of state 1 to the power N minus 1 over N, and all that minus 1. So for this process, we can substitute our values since we have all these values. So we'll substitute the values and suppress the units. So R is 0.2968 for nitrogen. The temperature, T1, is 1200 Kelvin. Again, we'll just suppress the units here. These are all in SI units. This is over 1 minus N, which is 1 minus 1.25. And this is all multiplied by P2, which is 200, over P1, which is 2000 kilopascals. And this is to the power 0.25 divided by 1.25. And that's minus 1. And so we get the boundary work per unit mass in this process to be 526 kilojoules per kg. Now we need the temperature of the final state. So the temperature of the final state is T2. And in a polytropic process, T2 is equal to T1 multiplied by P2 over P1 to the power N minus 1 over N. So this is equal to 1200 Kelvin, which is T1, into the ratio of the pressures to 100 kilopascals over 2000 kilopascals to the power 0.25 over 1.25. And so we get the temperature of the final state, T2, to be 757.1 Kelvin. Now let's go back to the energy balance equation. Divide both sides by M and solve for the heat transfer. So the heat transfer, Q in, is equal to the specific boundary work, little w, plus CV into T2 minus T1. Remember, we divided both sides by M. And now we've calculated the boundary work and we know the final temperature. So we can work out this heat transfer. So this is 526 kilojoules per kg plus CV, which is 0.743 kilojoule per kg Kelvin, times the change in temperature of 757.1 minus 1200, and that's in Kelvin. And so if we solve this, we get the heat transfer Q to be 197 kilojoules per kg.